Today we're going to look at scheduling with priority lists. So we're going to look at taking a scheduling diagraph and a priority list and creating a schedule from that. You will probably want to have some colored pencils with you for this lesson. First thing we're going to look at is a priority list. So a priority list is a list of all tasks prioritized in the way we prefer to execute them. So you'll have a list of tasks, and if X is before Y in the list, then we want to do X first, assuming that X is ready. Remember that ready means that all precedence relations have been satisfied, so all tasks that have to be executed before X have been done, so X is ready and can be started. The priority list model tells us that if we take every possible priority list, we can produce a schedule from each of those priority lists. Some of them will probably end up being the same, and then we choose the best one. So if we are going by brute force, which we talked about in the previous unit, where we find all possible priority lists, and then we choose the best schedule. The issue here is that we can produce a lot of priority lists. So if you have n tasks, you will produce n factorial priority lists, which is a lot. Most of the examples we've looked at so far have had 5, 6, 15 different tasks. So you can have a lot of priority lists. You do not want to have to create a schedule for each priority list and then compare them all to see which one is the shortest. So today we're just going to look at how you take a priority list and create a schedule. And then in the future, we will look at different algorithms for trying to find the best priority list. So let's go ahead and look at a situation. Before the launch of a satellite into space, last-minute systems checks need to be performed by the onboard computers, and it is important to complete these system checks as quickly as possible. We're going to assume that we have 2 processors and 5 tasks that have to be completed. So we have the project diagraph here. We have tasks A, B, C, D, and E. You can see all of the precedence relations from that diagraph. And then we're given this priority list. So if ready, we want to do task A first, task B second, C third, D fourth, and E fifth. So I'm going to go through this example in a lot of detail. I promise you will not have to do this much detail for all of the problems. So I have this little schedule chart here at the bottom. I have the first row for processor 1, the second row for processor 2, and then the numbers along the top are the number of hours. So we're keeping track of how long it takes to complete all of these tasks. So right now at t equals 0, things that are true. Tasks A, B, and C are all ready because they are the first tasks after our start vertex in the project diagraph. So if we look at the priority list says we want to do A first and B second. So we're going to assign A to processor 1, because that's what we're supposed to do first, and B to processor 2. So here's where the coloring comes in. A takes 6 hours. So I'm going to color in a 6-hour block for task A. And then I'm going to label that that was task A, and it took 6 hours. Then I'm going to assign task B to processor 2. So I have processor A working on task, or processor 1 working on task A, processor 2 working on task B. The next notable thing that happens is after 5 hours, so at t equals 5, B has been completed. So processor 1 is working on task A. Processor 2 has completed task B. So we want to ask ourselves, what tasks are ready? Well, the only task right now, B has been completed. That's it. The only other task that is ready is task C. So we're going to go ahead and assign task C to processor 2. So I'm going to draw that into my diagram. Okay, so then we want to look at what is the next significant point in time. At t equals 6, processor 1 has completed A. Processor 2 is working on C. So at t equals 6, both A and B have been completed, so task D is now ready. Since that is the only ready task, we're going to go ahead and assign D to processor 1. And I'm going to draw that into my diagram. So the next significant point in time is going to be at t equals 8. Processor 1 has completed task D. Processor 2 is still working on C. The only task we have left is E, but is E ready? If we look back at our die graph, C has to be complete before E can start. So E is not ready. We're going to have to wait. So processor 1 can't do anything right now. We have to wait until the next significant point in time, which is at 12 hours when processor 2 has finished task C. So now that task C is complete, E is ready. So we're going to assign E to P1. Technically, we could assign E to either of the processors, but convention says that you start with processor 1 if it's available. So at t equals 12, P1 can go ahead and start task E, which takes 5 hours. In this chunk of time, P1 sat idle. In this chunk of time, P2 will sit idle. And we will be done in 17 hours. So at t equals 17, we are at the end. So using this priority list, this is the schedule that we come up with. It takes 17 hours. But using a different priority list might give us a different schedule. It might give us a better schedule. So let's go ahead and take a look at the next example. If you want to continue to write out all of the details about what happens at certain points in time, you can do that. If that's not helpful for you, you don't need to. But I want you to go ahead and pause the video, try this problem on your own, and then I'll come back in a minute and you can check your answer. So, this is what you should have gotten if you did this problem on your own. We have a different priority list where we have E as our first priority, then D, then C, then B, then A. Again, at the beginning of this situation, A, B, and C are the only tasks that are ready. Since of those three, C is the first in the priority list, we're going to start with task C and assign that to processor 1. Then take task B and assign that to processor 2. So those can go ahead and start. At t equals 5, we have completed task B. The only other ready task is task A. So we can go ahead and have processor 2 start on task A. At t equals 7, task C is now complete, which lets us start task E. Because after C is done, then E is ready. So processor 1 can start working on E. At t equals 11, processor 2 has completed task A. So now that task A and B are both complete, task D is ready. So processor 2 can start on task D. At t equals 12, processor 1 has completed task E. There are no other tasks that need to be started. Every task is either complete or in execution, so processor 1 has to sit idle. Processor 2 finishes task D at t equals 13. So we are done with a final processing time of 13 hours. Now, a couple extra bonus pieces of information about this. If we look at the total time to complete all of these tasks, we have 6 plus 5 plus 7 plus 2 plus 5. That gives us 25 hours. With 2 processors, if I divide this by 2, that's 12 and a half hours per processor. So if I could divide these tasks perfectly in half between the 2 processors, it would take 12 and a half hours. But since all of my times are integers, I'm going to have to round that up. And 13 hours is the minimum time possible to complete all of these tasks, which means that this is actually an optimal schedule here. And if you look at it, it makes sense. Both of the processors are working the entire time. One processor finishes 1 hour before the other, but other than that, they're both working the entire time, and it seems fairly efficient. So this is actually an optimal schedule. Now, let's look at this situation with a third variation. What happens if we use 3 processors? Does that improve our final start time or final processing time? So again, if you would like to pause this video, try this problem on your own, and then I'll come back in a minute with the answer. So here's what you should have for your schedule using 3 processors and this priority list E, D, C, B, A. So to start, tasks A, B, and C are all ready. If we go by order of priority, we're going to assign C to P1, B to P2, and A to P3. After 5 hours, P2 has completed task B, P1 and P3 are still working. But there are no tasks ready because if you look at the project diagram, Both A and B have to be complete before D is ready, and C has to be complete before E is ready. So processor 2 cannot do anything. We have to wait. At t equals 6, when processor 3 has finished task A, D becomes ready. So we can assign task D to processor 2. At time equals 7, processor 1 has finished task C, which means that task E is now ready, and that is the last task that we need to start. So processor 1 can start on task E. T equals 8. We've finished task D. There's nothing else left to start. All tasks have either been completed or are in execution, so we need to continue to wait. And then at t equals 12, processor 1 finishes task E, and we are done. Our final processing time is 12 hours. Now, I will tell you that this is an optimal schedule for 3 processors because we talked in the previous video about the critical time. We have that C has to happen before E. So C takes 7 hours, E takes 5 hours. So at a minimum, we're going to have 12 hours to complete these tasks. So this is actually an optimal schedule here, taking 12 hours. But is it worth the investment? With 2 processors, we could complete this task in 13 hours. Is it worth the money to buy a third processor when it only improves our time by 1 hour? Probably not. So adding processors doesn't always give you enough of an improvement in your time to make it worth it. So you might be thinking, all right, this is cool, but how do I avoid having to write all of this information with t equals this all of the time? Well, there's some shortcut notations that we can use. If I just have the letter for my task, this means that this task is ineligible, okay, or not ready. If I draw a circle around the task, that means that it is ready and can be started at any time. If I put a slash through it, then the task has started, so it is in execution. And if I put the other slash through it, so I have a circle with an X, it means that my task has been completed. Again, this is just some notation that you can use. So let's take a look at one last example. Going back to our Martian habitation unit, we have 2 robots that are going to assemble the Martian habitation unit. We have our project diagram that is similar to what you drew in the previous video, just, little straighter lines and things. And then we have a priority list here. So let me show you what this notation looks like. So when we look here, the tasks that are ready are AP, AF, AW, and AD, because those are the tasks that come right after the start vertex. So based on the priority list, I want to start with AD. So I'm going to assign that to processor 1, and that takes 8 hours. Okay, so this is task AD, 8 hours. So that one is now in execution. Then the next ready task in my priority list is AW, which takes 6 hours. Oops. So this is AW, 6 hours. So I can ask myself, at t equals 6, what is happening? T equals 6, AW is complete. AD is in execution. What else is ready? Well, I know AF and AP are ready. Now that AW is complete, is AI ready? Or IW ready? No, because there are other things that have to be complete before IW is ready. So the next task I can start is AF. And AF takes 5 hours. Okay. So then again, I ask myself, at T equals 8, what is true? AD is complete, AW is complete, AF is in execution. AP is ready. Well, now that AF is done, is IF ready? No, because AP has to be completed first. So my only ready task is AP. So I can go ahead and assign AP to processor 1. And you can continue this. So pause the video here, try to finish up this schedule on your own, and then we'll come back together and check your answer. So if you go through all of these tasks and put them in the schedule, this is what you get. We have a finishing time of 44 hours. Processor 2 is idle quite a few times, and processor 1 is working the entire time. So in the next video, we will talk about how to find a good priority list that will give us a decent schedule.